All right, so today we're going to talk about section 4.3, analysis of functions, rational functions, cusps, and vertical tangents. In the last couple of days, we've been just analyzing our basic functions. Today we're going to start analyzing our rational functions and additional functions. All right, so a couple of things that we want to point out. The first one is that all of these steps up through step 5 are all pre-calc or algebra 2. Okay, so we want to talk about symmetries. We want to talk about x and y intercepts. Remember that setting either x or y equal to 0. Vertical asymptotes are where the denominator is 0. We want to talk about the sign of f of x. That's where we need to look at those vertical asymptotes and our intercepts, because that's the only place that it can go from positive to negative. And then we want to talk about end behavior, which is limit. And that is going to be from our pre-calc. Okay, the last two steps are the calculus, the derivatives, first and second derivative tests that we discussed in section 4.1 and 4.2. And then we want to be able to conclude what's happening with our graph. So we're going to look at the first and second derivative tests, and we're going to determine whether the function is increasing, decreasing, concave up, or concave down. And then we're going to look at the first derivative test to figure out if we have any station points. We're going to look at the second derivative test to figure out if we have any inflection points. And then we're going to look at our relative max and minimums. And remember, those are where the first derivative is set equal to 0. Okay? So let's go ahead and do an example. I've put a graph on my page. And so we're going to sketch a graph of the equation. So the first thing we want to do is factor it out, because that helps us to see all the little pieces. And so I'm going to take a look at the denominator, and since I can't reduce anything, I'm going to go ahead and put my vertical asymptotes at x equals 4 and negative 4. I'm going to come up here to the original equation, and I'm going to look at my largest degree, top and bottom, and I'm going to look at the relationship between those two. And I'm going to see that I have a horizontal asymptote at y equals 2. And then what I'm going to do is I'm going to set my x equal to 0. So I'm going to pretend like this isn't here. And I get negative 8 over negative 16, which is 1/2. Now I'm going to look at my numerator to find my zeros. So negative 2 and 2. So in the middle, I'm going to go something like that. And now I need a point to the left and the right of my vertical asymptote so I can see where I'm at. So I'm going to just go ahead and plug in negative 5. Which gives me 2 times negative 7 times negative 3, which is 2 times 27. On the bottom, I'm going to get negative 9 times negative 1, which is going to go ahead and give me 9. 9 goes into 9 once, 9 goes into 27 3 times. So 2 times 3 is 6. So when I plug in negative 5, I'm going to get 6. So this is going to go something like that. And then I'm going to come over to the other side and I'm going to plug in 5. And if I plug in 5, it changes those signs. If I plug in 5, it changes those signs. So I still get a positive 6. So 5 and 6, and I'm going to get that function. Okay, so the first few problems, we're just going to be sketching the curve. All right, go ahead and pause now and attempt this one on your own. I'm going to go ahead and work it here. And so the bottom is bigger. And I'm going to have vertical asymptote. At x equals 0. And now I want to take my graph and I want to say, let's choose a number to the right and left of my asymptote. Okay, so you are, I hope, working on this on your own as well. And so I have a horizontal asymptote. Oh, my bad. I drew that wrong. So I have my vertical asymptote is at y equals 0 because that's going to be 1 over x. So let me draw that and label. And I have a vertical asymptote at x equals 0 because that's the only number in the denominator that's going to make me have issues. And then I want to take my graph and say, okay, well, what's happening to that? And it turns out that when I look at my x and y intercepts, they're actually on my asymptote. And one of the things that we say early on in Algebra 2 is, oh, you can't ever cross an asymptote. And that's not entirely true. You can't cross an asymptote out at infinities. But when we're on the small scale, you can, in fact, cross the asymptote. And so this is actually going to come cross, and then it's going to approach 0 that way. And the same thing is true here. I'm going to cross the asymptote, but then I'm going to head that way. And you can see on both sides, I'm actually approaching 0. However, I do cross at 1 and -1. Okay, those, if I plug in 1, you can see I get 0. And it doesn't pose a problem for the denominator. It only poses a problem out on the ends. Okay, so don't freak out if you see that. That's actually what you're going to get. It is going to cross the asymptote on a small scale, but on the ends, it is going to approach 0. Okay, so if you have vertical tangents and cusps, a couple of things. Right here and right here, you're going to have a vertical tangent, which we know vertical tangents are undefined. But let me remind you that on those places, that function is not even differentiable. Remember that? So back in chapter 2, we talked about differentiability. The problem is the slope coming in from the left and the right will never be equal. At that cusp, you're going to be not differentiable. Okay, so again, it's also undefined. Okay, so sketch the graph x minus 4 to the 2/3. So for me, it helps if I write it like this, so then I can understand what kind of parent function I'm dealing with. I'm actually dealing with a cubic, or a cube root, I should say. So I'm going to go ahead and get a graph. And my 0 is going to occur when x is equal to 4. So I know I have that. And I'm also thinking we have two things. We have a cube root function, which I kind of know what that looks like. I also know that this means it's shifted 4 to the right. And if I know that, that also helps me get a better picture if I know my parent curves. And so one of the things I'm hoping is that when you do this, if you're at all confused, you can go ahead and pull out your graphing calculator and take a look at what that looks like. But for the most part, we should know what our parent functions are going to look like, and we want to be able to draw those accordingly. So I don't have a denominator, so I have no vertical asymptotes. I have no horizontal asymptotes. Cubic functions or cube root functions do not have domain restrictions, and so I have no numbers that I can't plug in there. You can have a negative cube root. And so now what I want to do is I just want to plug in some points. So I'm going to plug in 3 of the easiest ones that I can find. And I also want to remember this. If I square something, it is always going to be positive, no matter what. So my answer is never going to go below 0 in the y direction. It will never be negative. It will be positive everywhere. So if I plug in 5, I get 5 minus 4 is 1. 1 squared is 1. The cube root of 1 is 1. If I plug in 3, I get 3 minus 4, which is -1. -1 times -1 is 1, and the cube root of 1 is 1. And so now I know I'm going to go like this, but I want to find where I'm going to touch my y-axis. And so what I need to do is I need to set 0 equal to the cube root of x minus 4 quantity squared. So to undo this, I'm going to cube both sides, undoing operations. And now I'm going to square root both sides. So now I've cube rooted both sides. Oh, I'm so silly. Yeah, I did this already. X equals 4. Miss Collins, you silly goose. The second thing I need to do is plug in x equals 0. Oh my word. 0 minus 4, quantity squared, becomes 16. And the cube root of 16 is going to be more than 2, but less than 3, so about 2.5. This is the exact answer, the cube root of 16, but I'm going to go somewhere bigger than 2, but less than 3. So I'm going to go like this, and there we go. We're good to go. Okay, so all we're doing is sketching a graph. Important points, we want to have our zeros, our intercepts, and we want to know what's happening with the function. Okay, sketching the graph of 6 times the cube root of x plus 3 times the cube root of x to the 4th. Okay, so what we're going to do is we want to take this and we want to say, okay, what can we do to that? We want a picture. And that to me is just ugly. And so I would either do a t-chart or I would do just figuring out where my intercepts are and then go from there. One of the first things that I want to know is this one can be negative at some point. This one will not ever be negative because I'm going to take the 4th power of something. So no matter what number I plug in there, it's always going to be positive. So I want to start with a picture. Oop, my bad. Let me move that over. So I'm going to go ahead and take my picture and I'm going to move it to the side so I can do some stuff with it. And the first thing I want to do is say, okay, what happens if x is 0? If x is 0, y is 0. So if I plug in 0, that's gone. Plug in 0, that's gone. You get y is equal to 0. The second thing that I want to do is I want to say, okay, if I do that, then is it only going to touch y in one place? So I set x equal to 0. Now I want to set y equal to 0. So if I set y equal to 0, I get 6 times the cube root of x is plus 3 times the cube root of x to the 4th. And so 3 cube root x to the 4th is equal to 6 cube root of x. And now I want to cube both sides. So now I'm going to get 27x to the 4th is equal to 216x. And so I want to pull out the greatest common factor. Is it 9 or 3? Is it just 3? Let me take a look. I'm doing math in my head. 21 divided by 9 is 2, 36, 14. Okay, so I'm going to take out a 9. And I'm going to get 3x cubed minus 24. And so it's going to happen when x is 0. It's also going to happen when x cubed equals 8, and that's going to be when x equals 2. So those are the two places that it is going to touch my x-axis. And now what I want to do is say, okay, let's take a look and say we need a test point on either side of my zeros. So I need one at -1, 1, and 3. So if I plug in -1, I'm going to erase this so I can see my function. If I plug in -1, I get 6 times -1 plus 3. So when I plugged in -1, when I evaluated at -1, I'm going to get -3. So -1, -3. And then when I plug in 1, I'm going to get 6 times 1 plus 3 times 1. And I'm going to get 9. So when I plug in here, 9 is off. So that's okay. And then when I plug in 3, I kind of want to plug in a number that has a cube root. And I don't have one on my scale. But what if I plugged in 8? Okay, what if I plugged in 8? Well, the cube root of 8 is 2. So I'm going to get 6 times 2 plus, now what's the cube root of 8? It's 2, and 2 to the 4th power is 16, and 16 plus 3, or 16 times 3 is 48. So this is going to be 60. So that's going to be way big. So going up, going up. What number did I plug in? Oh, I plugged in 8. It's way, way up here at 8, comma 60. And so now I need to make my graph work. And so what I want to do is I want to say, okay, if I need more test points, I want to go ahead and do more test points. Okay, so I'm going to pause right now, and I want you to do some test points if you can. So go ahead and do a couple of test points. Okay, so I'm hoping you have some test points. I also have some test points. And so one of the things, as I was standing here looking at the screen, I realized Ms. Collins did some bad math. When I moved this over, I dropped a minus sign. So that minus sign right here is going to affect one number, and that's this one. And so due to my bad math, I have my intercept in the wrong place. It's a good thing I was paying attention and paused. So I get a -2 here because these are all off by a minus sign. Okay, so bad Miss Collins. Okay, so let's just erase that one. So I'm off by a minus sign, and so I want to make sure that I corrected that. 3x cubed minus, where did I go? 24, thank you. Okay, so when I moved the 3 over, I have a minus. So when I cubed it, I needed this minus sign here. Okay, and so that throws everything off by just a tad. So I apologize for that, but that affects my test point. But it does make my graph a little bit easier to draw. And so now I realize that I'm coming down like this, and I'm going to hit, and remember, I'm off over here. The scale is off, but it's going to go up like that. And because we're sketching, if my curve function, I mean, this could be steeper here, it could be steeper here, I don't know, but I'm just sketching. The important piece is that I have my dots in the right place. Okay, so that's why it's good that I pause so I could find that error. Okay, next example. Okay, when we're graphing an exponential or a log, those are special functions. And so we want to remember that negative exponents really mean move it to the bottom. Okay. And so in that case, I realize a couple of things. My graph is never going to be 0. It's never going to be 0. It is always going to be positive. I need to remember that exponentials typically had a horizontal asymptote at y equals 0 because they're never going to be there. And so when I look at this, these are always going to be fairly small numbers. And the reason is I have that x squared on the bottom. So even if I plug in a negative x, I'm still going to get a positive value. Okay, now I'm also being asked to do two things. Not only am I being asked to sketch the function, but I'm also being asked to define all relative maximum and minimum, okay, or minima, if you will. And so what you want to make sure you're able to do is, first off, sketch the function. You want to sketch the function, okay? And that becomes the most important part. And so we want to remember, the first thing is I'm going to pull up a graph because I want to have a graph. So I'm going to make enough mistakes without the graph. Let's at least include the graph. The second thing I want to note is the biggest this value is ever going to be is 1. And here's how I know that. When I take a look at this exponent, if I plugged in x equals 0, I get e to the 0, and e to the 0 is 1, and 1 over 1 is 1. I also know that I'm never going to approach 0. I'm never going to hit it. So I'm going to approach it, but I'm never going to be there. So that's a horizontal asymptote. If I plug in -1, I get e to the 1/2 and 1 over the square root of e, somewhere here. And it's going to be the same on either side. And the reason I know it's the same on either side is because this x squared is going to give me symmetry over the y-axis. Okay, so when I'm doing that, I want to kind of pay attention to that because I need to know what's going to happen. And so I haven't done my derivatives yet, and so I'm sketching at this point. I know these dots are going to be getting closer, but I don't know whether it's concave up or concave down. And what I'm saying is I don't know if it's going to go like this or if it's going to go like this. Okay, so I need to know my concavity, and so where those changes happen. And so now I want to take the derivative, and I'm going to take the derivative from right here. And the derivative of e to the anything is e to that thing times the derivative of that thing. And so what I end up getting is negative x e to the negative x squared over 2. So negative 2x divided by 2 is still going to be negative x. And so here's my derivative. And now this is always going to be negative when x is positive, or positive when x is negative. And so when I look at this, I go, okay, that means my function is going to be increasing when x is negative and decreasing when x is positive. So I know that because the only place this is going to change sign is 0. So if I plugged in a negative 1, I'm going to get these kind of values. If I plug in a positive 1, I'm going to get these kind of values. This says f is increasing here and decreasing here. That would make sense because my values are close to 0 and I'm coming up, and then my value is going down. Okay? So the second thing I need to do is a second derivative, which means I'm going to take the derivative of the first derivative. So right here, I'm going to take the derivative of that. So the derivative of the first times the second plus the derivative of the second times the first. And that's going to get me negative e to the negative x squared over 2 plus x squared e to the negative x squared over 2. And so I'm going to factor and solve. So I'm going to pull out a negative e to the negative x squared over 2 from both. And I'm going to get 1 minus x squared. And that means x squared equals 1 and x equals plus or minus 1, which means my concavity changes at plus or minus 1. And so what I want to do is second derivative test, choose a number between them, choose a number to the left and the right. And remember, those are my thinking bubbles. You can pick any numbers you want. Okay, so here was my first derivative test. Here's my second derivative test. And so when I plug in negative 2, if I plug in negative 2 right here, I'm going to get a negative number. Okay, so concave down. If I plugged in negative 2, oh, my bad, I get a positive number. A negative times a negative, positive. So this is a negative. If I plug in 2 in here, I get a negative. So a negative times a negative is positive. When I plug in 0 here, plug in 0, I get a positive times a negative, it's negative. And when I plug in 2, I get a negative times a negative, which is positive. Now that tells me that I'm concave up. So now when I come up here, I realize this has to be going up. So like catching water, and then it curves at this point, and then here it's now, so concave up, concave down, concave up. Inflection point, inflection point. Now we find our maximum and minimum by setting our first derivative equal to 0, which is the same way we do our first derivative test. So when we set that equal to 0, our first derivative equal to 0, that's where we're going to have a horizontal tangent, okay? And the only place that's going to happen is at 0. And so right here, we have our relative maximum is at x equals 0. And when I plug in 0, then I'm going to get 1, okay? So at x equals 0, so I found the x value where that happened. Now I plug that into the original equation. Okay, I'm not plugging it back into the derivative except for the derivative test. All right, next example. So using calculus and a calculator. Okay, so here's what we're going to do. Go ahead and grab your graphing calculators. If you don't have a graphing calculator, I hope you have an app. And we're going to go ahead and enter the natural log of x. So natural log of x divided by x. So I have mine entered, and I'm going to go ahead and graph it. And you should see basically a log graph. Oh, here it is. And they want you to actually change your window so that your window is -1. Look at here's they're telling you your window. And so if I go to my window, you're going to change your window from -1 to 0.25. And then you want to go, you want to be counting from, so my bad. So then you want to count to 25. Silly girl, Miss Collins. Delete. 1 to 25. And then you want to be counting your X scales, counting by fives. And then your Y, you want it to go from -0.5 to 0.5, and you want that to be counting by 0.2s. And now when I graph it, I get exactly that picture. So if you didn't get it, again, we're using the technology. You've got to understand what we're saying here. So that was a comma, not a minus sign. So we want to go from -1 to 25 on the X direction. And then we want to go from -0.5 to 0.5 in the Y direction. Here's the important things. We know logs cannot exist when X is negative, but by putting in a negative here, we can see what's happening close to the Y axis, okay? And so now what we want to do is we want to have you take a look at where your relative max and min are, your extrema, your relative max or min, your inflection points, your asymptotes, and the end behavior. So a couple of things that you should know. You're going to have, in this case, you're going to have a horizontal asymptote at some point. You don't know where it is yet, although you do. You just don't know it. And then you're also going to take a look at your x-intercepts. You're also going to have a vertical asymptote. So the denominator cannot be 0. Neither can the numerator, actually. You cannot plug in the natural log of 0. It doesn't work. And so 0 becomes your vertical asymptote. And then what we want to do is we want to take some derivatives and see what happens. So we're going to take the first derivative, take the derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. So we're going to get 1 minus the natural log of x all over x squared. And I want to know where that is going to be a max or a min. Well, that's going to happen where 1 is equal to the natural log of x. So we're going to e both sides. So we get e is equal to x. So that's actually going to occur, your max or min is going to occur when x is equal to e. So I'm going to take e and plug it back into the original equation. So my max is actually at e comma 1 over e. Now how do I know if that's a max or a min? Well, I come over here and I plug in e. I do just what I would have done before. Now I can't be 0, so I'm not going to plug in 0. So I'm going to plug in 1 and 3. Those are right and left. So I need my calculator. And so what I'm going to do is I'm going to plug in 1. So the natural log of 1 is 0. So I get 1 over 1, which is positive. Now I'm going to plug in 3. So I'm going to get 1 minus the natural log of 3 over 9. That's x squared. And so I do that on my calculator because I don't know what the natural log of 3 is. I'm sure Mr. Clinton does. Human calculator. It's actually just above 1. So I'm going to get that. And so what this says is since f is increasing and here f is decreasing, this point right here has to be a max because I was going up and now I'm going down. Okay, so E is the max. Now what I want to do is I want to take a look at my inflection points, and that means I have to take a look at the second derivative. Okay, so second derivative means take a look at the first derivative and take the derivative of that. So 1 minus the natural log of x. So what's the derivative of that? It's going to be negative 1 over x times the bottom minus the derivative of the bottom, which is all over the bottom squared. So I can see some simplification happening here. So I'm going to get negative x minus 2x plus 2x ln x all over x to the fourth. So if I do a little bit of algebra, hopefully I'm doing it correctly. So I'm going to factor out a negative x, and I'm going to get 3 plus 2 ln x all over x to the fourth. Gone. So I get negative 1 over 3 plus 2 ln x over x cubed. So doing some work here, I want to set that equal to 0, which means negative 3 is equal to negative 2 ln x, or don't do that, Miss Collins. Let's erase it and show you my work. I have this on top. So negative 2 ln x is equal to 3. So where ln x is equal to 3 halves negative. Correct? And so I need to solve that. And so if I do that, I get x is equal to e to the negative 3 halves, which is equal to 1 over e to the 3 halves. That means e cubed square rooted and then 1 over that. And so now I know where I have a change in concavity. Okay, a change in concavity. Now that change in concavity, if I look here, I should see it looks like it's concave down, and now it's looking like it's concave up. Okay, so I want to check for a math error because I'm sure I have one. That number seems too small to me. So derivative of the top times the bottom minus the derivative of the bottom times the top. Let's make sure I did this right. And then a minus and a plus. And distributed that, and then I get a negative x minus 2x. So it looks like I don't have a math error, but I think I do somewhere. I'm just not sure where that is. So negative makes that negative. When I add it to the other side, I get a positive divided by a negative. I'm thinking I dropped a minus sign somewhere. I'm going to go ahead and check it on my calculator. So if you'd like, you can go ahead and pause now. I'm actually going to do a little calc with my calculator. And so I'm going to go ahead and enter my first derivative, which was 1 minus, and you can do this on your calculator, 1 minus the natural log of x on top divided by x squared on bottom. And I want to see what that looks like. Oh no, that appears right. And then I want to do that at x equals 0, evaluate the first derivative. So second calc, 6, and it's 0, and it's going to give me a number. Awesome. Okay, so that's what you're doing. I checked it. We're good. Okay, so use calculus to find the key locations. So you can use the calculus. When you come into class tomorrow, we'll actually do the calculator in person as well. We don't all use the same kind, but it is extremely helpful if you use your calculator, because what ends up happening is, in case you see there's a math error, you can go back and find that. So I'm going to pause here for just a sec and double check my math, because I'm concerned I do have a minor math error. So, okay, double check my math. I can't find an error. I'm sure it's there. Double check me. I'm confident I did good math, but I might have missed something. All right, next example. These are for you, and what you want to make sure you do is your quick check, and they're not so quick this time. One of the things you're going to see is Mr. Clinton has so nicely written, these are actually slow check. There is a lot of them. Okay, it is very important that you show your work. These are on page 263 in your book, and the answers are on page 266. Please show your work, and please come to class with some work on your paper and questions. Okay, good luck.